Okay, welcome back, Physics 20s, to our continuation of looking at some fundamental math skills that we'll use for physics. The first part of the worksheet is for you to actually do some practice with formula rearrangement and order of operations and unit conversions. So pause the video, give a try with those, and we'll come back for the answers. Okay, so hopefully you had enough time to do those. Let's see how you did. So plugging this into your calculator, reminder that it's the entire numerator over the entire denominator. I put the numerator in first, so 5 plus 2, which would be 7 squared, 49, over 6 times 3, which is going to be 18, should give you in your calculator 2.72 repeating. We'll look at significant digits later. Hopefully you can get to that value. Similar to the next one, not a very complex numerator, just with 45. But divide by all this in brackets. And when you plug that in, that should give you 0.3. Nice number there. Okay, next look at formula rearrangement. This one looking pretty simple, but the idea we're stressing here is that if x is in the denominator, get it out of the denominator first by timing by x, and now it's out of the denominator. We can just solve for it by itself. And it's being multiplied by 10, so we'll divide by 10 to move 10 to the other side. 45 over 10, x is equal to 4.5. Okay. The next one, x is not in the denominator, so I don't have to move it. I could solve for just what x is, but there's actually a negative with it because it's minus 2x. So I will be solving for negative x if I keep it there. You can totally do that, but I like to work with positive x. So I'm going to want to move it to the other side. Again, because these brackets here, I'm going to deal with the denominator first, just like I did in the last case. So we'll multiply the 6 on both sides, and that's going to make this 48. Okay, now that I'm just left with the 5 minus 2x, I want to make that negative 2x positive, so I'm going to plus 2x, and write 48 plus 2x is equal to 5. Again, not necessary, but it makes the x positive, which I like to work with. Next, we'll do our reverse order BEDMAS, get rid of the 48, addition, subtraction. Minus 48 gives negative 43. 2x equals negative 43. Divide by 2, and that should give us negative 21.5 for our value of x. Okay, so if you just didn't make this positive off the start, you would have gotten negative x is equal to 21.5, and just move the negative at the end. So either of those are fine. Okay, so one last example here, looking at the unit conversions. There's two ways to do it. The way I probably prefer is just starting with your value of 200 pounds and going into kilograms, knowing that, well, looking at my ratio, pounds should be a bigger number than kilograms. So I need a smaller number as my answer. To get a smaller number, I put the conversion here, 2.22. Timesing by 2.22 would give me a bigger value, so I'm going to divide by 2.22, and I get an answer that's smaller. I believe it's 90.09 repeating there. Okay, if you want to use the unit canceling method, that works just as well. So I am looking for my answer in kilograms. So I'm going to write my ratio with kilograms on the top and the pounds on the bottom. So 1 kilogram is equal to 2.2 pounds. If I times by 200 pounds, pounds cancel out just like they do with algebra. I have 200 divided by 2.22, and you get the same number, 90.09 repeating. Okay, so hopefully those went well for you, and next we'll move on to the new lesson for today. The first skill we're going to look at, and really the main skill for today, is actually looking at graphing. I know graphing, not necessarily the most popular, but maybe one of the most applicable to math and science courses. Both creating and reading and even predicting what a graph is going to look like are things that are going to come up in this course. So let's start with creating. I know it might seem easy just to put points onto a graph, but this is the first step for analyzing an experiment or a lab, or even a question given to you on a test that was about a lab. So it's really important that we get this process right. First thing, a common mistake I see students do is they use inconsistent spacing, meaning their first square was worth 2 and their next square was worth 3. that throws the whole graph and you probably won't get any marks for it. So make sure it's consistent. Space your numbers reasonably. So if you have a graph, it should approximately take up like the majority of the space. You don't want just a little line at the bottom corner that's hard to read. So spread them out reasonably. Title, axes, and units. The title isn't overly important, but the axes and units definitely are. So you have to put the right values on the right axis. Your X goes here, your Y goes here, and you have the correct units. This is going to apply to things like your slope and area. So maybe if X was our time measured in seconds, you have to plot that. And Y was our position measured in meters. We would have to label those so that we know that we're graphing the right things. Okay, but right now we're looking at how to accurately put those numbers on. We haven't looked at actual numbers like with units, just given an X and Y chart. Okay, so I try to make some that are not too difficult, but also not too simple, so it kind of shows the process. Let's try and plot these correctly. Okay, so first I'm going to begin with my X, and we have to know that X is the horizontal axes, and it looks like my numbers go from 17 to 58. So looking at the graph, I want to reasonably slice those out and make it so each line is a kind of easy number to estimate. You don't want it to be like 0.358 is every single line. That's hard to estimate. So for this one, I think it'd be easiest to go. Let's see how many lines we have. 1, 2, 3, 4, 5, 6, 7, and we need to get just about to 60. So let's just do each one as 10. 20, 30, 40, 50, 60, 70. Okay, it goes a little bit farther than I need, but that's okay. Next, looking at our Y, it goes from 56, I can say 0 to 56 to 520. 1, 2, 3, 4, 5, 6. So I think I'm going to do similar. I'm going to just go up by hundreds here. Make it fit really easily. All right, and if I'm going too fast at any point, please pause and make sure you can catch up, as I will be a little bit quicker in these video methods rather than in class. Okay, now with those nice spacing, as much as those numbers are good, the other thing you have to consider is that each line is good. Like again, I don't want this to be some horrible decimal. I want it to be nice and easy to estimate. When I'm putting my points on, they're easy to plot. And this does work out well. It's just 2, 4, 6, 8. Those are nice, easy numbers. You don't have to write them all in, but good to know what each line is. We're going to put the points on here, which is our next step. So first I need to look at 17. So looking here, that's 20, that's 18, this is 16. That's my first point, about halfway between there. I like to put a little marker. 17 and 56. 56 is a bit trickier. This is 40 and this is 60. 56 is a little bit closer to that 60 line. So maybe out there will be my first point. Okay, next one, 29 and 127. 29, well this is 28. So about halfway will be 29. 127, this is 120, this is 140, so closer to that 120 line. Looking to me like it'll be about there. Okay, well, just about halfway, which would have been 130. Next one, 42, that one hits right at this line pretty well, and 444, this is 420, that's 440, so just a bit above that, as the next one's 460. 444, let's go just above that 40 line. I know there's the thickness of the dot, but hopefully the center of the dot's about at the 44 there. And the last one works out pretty well, 58 and 520. Let's scroll over to 58 right there. Make it big as I'm gonna scroll over to 520 there. Make sure I hit that correct matchup right in the middle of that point. Okay, so plot your points similar to that, and once you've done that, I want you to give a try kind of spacing out your points and plotting them on the next example. So give that a try, and then we'll come back to see how you did. Okay, so hopefully your point's looking similar to this. It doesn't have to be exactly spaced like mine was. I chose up to go up by 0.5 for each thick line, which made each line 0.1 on the x-axis and go up by 25s on the other side, which made each line 5. So 5, 10, 15, 20, 25. So it worked out pretty well for my graph. Hopefully you found a good spacing method and your overall trend looks similar, because now we're going to look at calculating what the trend is, and this is also called the slope. Slope can be used a lot in physics, and it's hopefully a little bit familiar with math, or from math, and it means the rate of change. It's going to tell us how one variable is changing related to another variable. So distance compared to time, velocity compared to time, force, things like that. Okay, so we're going to use it a lot. How you calculate it, and hopefully you saw it in math, was rise over run. So we're calculating how much goes up in the y by crossing the x. It's really important to consider our units to determine what the slope means and to make sure we have the right values there. So what I mean by that is if we look at the axes here, and this goes up to 3, let's say I had a run of 3. If the units was times 10 to the 2 meters, I have to put my run as 3 times 10 to the 2 meters, 300 meters, which would give me a different answer than using 3 meters. So make sure we look at the axes there. And the other point is a caution about counting squares. So first, I recommend that you probably don't count squares. And what I mean by this is just look at your first and last point and figure out their values, then use subtraction. But I have seen some people counting squares from their math courses, and that is okay, but you can't forget to multiply by what each square is worth. So for example here, if this was my run, this blue line here, and I said that's 1, 2, 3, 4, 5, and used a run of 5, that would be incorrect because it's 5 squares, but each square is worth 0.1. So my run would actually be 0.5. So what I think gets you there easier without tripping up is just take the difference from 0.5 to 1. Oh, that's 0.5. Might be a better way to find your run. Okay. And the last part on here, or last 2 parts, is don't always go to the origin. So don't always go to 0.0. You have to make sure you're using the points on the line. Don't always go through the origin. And if your points don't line up in a straight line, we're going to draw a line of best fit. It shows the overall trend of the experiment, because usually an experiment's not a perfect line. It'll show the trend, and then we'll find the slope of that. It's easier to show that than putting it in notes. So let's take a look at an example. And we're going to go back to this first graph that we saw. It's a bit hard to do on the tablet here, but your line wants to show the general trend and be as close as possible to the points. So I'm going to put my ruler on the screen here. It might not work perfectly. I'm going to draw a line through the data. Okay, so that's decent. How you can kind of evaluate it is that it's kind of as close as you can get to the points. So if I went a little more flat or a little more steep, it would be pretty similar. And this point's a little above. This one's that far below. This one's that far above. This one's that far below. So I might have some a little bit too far below, but it's decent. It's not bad. Okay, so that's the line of best fit. If our graph isn't linear, which this one wasn't, it was all zigzaggy, we draw a line of best fit like that. And now we have a line that we can find the slope of. Now I need to calculate rise over run. You might be thinking, where do I use the points for rise over run? Well, I need points that I can read easily, and I want them fairly separate. So I'm gonna look at the first top of the graph, the top of the graph, and look for points that intersect well. And actually I'm pretty lucky. I have a good one right here. That's crossing right at those lines. So I can say the value of that is here and here. I don't have to estimate halfway between a square. So that's a good spot. And I don't want another one really close to it. I'm gonna look at the bottom part of the graph, see if I see another one of those. Looks like it's already a bit trickier to find one here, but this one looks pretty good to me. It intersects there and there. So now I have to have those nice intersection points. I can read what the rise and run of this will be. And I recommend looking to the side. So this is 580. And this one here is 160. So 580 minus 160 is going to be 420 for my rise. 420. And looking at my run, this point was 26. And this point was right on 60. So that becomes 34. So my rise, 420 over 34, throw that in the calculator, is about 12.4, and that would be my slope. You know, you might not be getting exactly 12.4 because your line of best fit may be slightly different, and the points that you chose are probably slightly different than mine. So hopefully you're getting somewhere between 12 and 13 would be probably fine for this one as we're getting used to this method. So give it a try on that one. Hopefully get close to 12.4, and then give it a try on the next one as well, the one that you did here, and then we'll come back and see how you did. Okay, so taking the second one up, just showing my line of best fit. Again, yours might be slightly different, but I'm really close to that first point, but that far for my second, that far for my third, and that from the fourth. So pretty close there. I'm happy with that. And then I found two intersection points here that line up with 110 and 40. So a rise of 70, and then it went from 0.5 to 2, so a run of 1.5. I'm going to recommend that instead of counting squares. 70 over 1.5 gave me 4.6 repeating for a slope. Hopefully maybe yours was between something like 4.4 and 4.8, or maybe in 4.2 to 5. Something like that would be reasonable for the slope, and hopefully getting used to this method, and we'll be applying that to some graphs later on in the course. Moving on to the next section of this lesson is now to look at area under the curve. It's actually kind of similar, but instead of looking at rise over run, it's looking at rise times run. So this is the area under the graph drawn to the x-axis. That's important. So you basically make a shape drawing straight down from your line to the x-axis. It's often a triangle or a rectangle and a triangle. Okay, so you find the area of that shape, base times height for triangle, base times height divided by 2 for triangle, base times height for rectangle. So I'll quickly show what that often looks like. Often looks like this. We have a graph going up, and you shade in the area under the curve to the x-axis. Base times height divided by 2 for that to solve the area. Okay, sometimes the shapes are a little bit harder, so I'll give an example of that. Maybe your shape looks like this, doesn't begin at the origin, and when you shade in the area there, it's not a rectangle or a triangle, but we could break it up into a triangle and a rectangle. Maybe the area of this one was 3, the area of this one was 5, so let's say the total area under the curve is 8. Okay, that's area under the curve. Note at the bottom here, if you're going below the x-axis, those values will still shade up to the x-axis, and those will be negative. So again, harder to say with words, easier to show with a picture. So let's see what that looks like. Find a graph that was going down. Maybe like that. The first part, very similar. Shading in the area in the curve. Maybe I shade that in, and it's a 5 for the area. Then here, I don't actually shade down. I shade up. Again, I go to the x-axis. And maybe I get that to be a number of 4. As it says here, below is going to be negative, and above is positive. So that would actually be negative 4, because it's in the negative section of the graph. This one's in the positive. So the total area of a 5 and negative 4, the total area under the curve would be just 1. Okay. So I wanted to do an example of this based off the same graph, but normally it gives you a straight line, like these examples I'm showing here. So I'm just going to imagine that the line of best fit that we drew was the line that you were given. Okay. And it could say, like, for a certain time period, determine the area under the curve. So here, maybe it says from 30 to 40 seconds, you'd find this area if seconds was on the x-axis. That could be an example of a question. But let's just do the whole area under here like it's one big triangle. It's going to be a little bit tough to estimate sometimes these values where it intersects the x-axis. But let's just do an example shading this all in. All right, probably made sense with the easier numbers, but we'll try to apply it to this as well. So I shade in all the way down to the x-axis, and now I'm going to look for Oh, actually, I missed one. Went a little bit further. We said x-axis. There we go. The entirety of the line. So if they gave us that line, we're finding the area under the curve. I look from point here, which is a bit tough to read. Let's just estimate that it's 62. And this to be about 13. So the base there being 49. I know it's a bit tough to estimate on this one. It would be a bit easier on a normal graphing question. And then going all the way up to the top of 600 for our height there. So base 49 times our height of 600, divide by 2 because it's a triangle. And I'm getting a number of 14,700. So if you could just give that a try on yours, see where it intersects down here on your X and up here at the end of your line. Try and find the base and the height, divide by 2 and figure out what your area is. Again, hopefully it's similar to mine because it's got a similar slope. But yeah, because I know this one's a little bit more tough to interpret. It might be a little bit more off. No worries. We're just kind of get that principle of area under the curve down. Try that to your next one as well. See if you get a similar number to me, and then we'll be on to the last part of the lesson. Okay, so the answer for this last one, again, yours can be a little bit different. We got a little bit of a different shape for this one because we had the rectangle on the top here. I'll just kind of highlight that in red. That was the rectangle. I had that going from 20 up to 150, so my rise or my height of 130 and 2.9 for the base. So that gave me, I divide by 2, 188. And then I had a rectangle at the bottom here. The piece left over there with 20 by 2.9, which gave me 50.8. So total there, 246.5. Again, there'll be some variation with my answers and yours there, but hopefully somewhere close to that. And again, just trying to get the principle down. It would be not really common for you to see a line of best fit area under the curve question, but just trying to show the concept here. So hopefully the concept's making sense for shading in underneath the slope. And now we'll move to, I believe, the last part of the lesson here, looking at scientific notation and using your calculator. Something that's probably familiar, but is going to be important as we're going to use some really big and pretty small numbers. So scientific notation used to write something that is large or small with times 10 to the something. If you use a positive exponents for really big value, so something like 12,000 would be written with a positive exponent. Actually, I just have an example there below, so let's jump to that one. And how we're going to write that. So we're going to write it by moving the decimal place over. Let me just get a smaller pen. To the ones position. So right now, even though we don't put a decimal, the decimal's right there. We're going to move it over to the ones position. So I have to move it 1, 2, 3, 4, 5 positions. And I write this as 1.2. Okay, it moved over 5 spots, which is equivalent to 10 to the 5, right? Which would be equivalent to, oops, sorry, I forgot one there. 10 to the 5, 100,000. So it's 1.2 hundred thousandths. That's 120,000. So it's being the same as 1.2 times 100,000. So I'm going to write 10 to the 5. It's got 1, 2, 3, 4, 5 places there, kind of 5 0 spots. Okay, or multiples of 10. Okay, 1.2 times 10 to the 5 for that one. We put it positive when we move the decimal to the left or for big numbers. Here we have a small number, and it's going to be the same process, but now I'm just going to put a negative exponent because I have to move it the other way. 1, 2, 3, 4, 5. So 4.54 times 10 to the 5, but I put it as a negative because we moved it the other way, and this is a really small number, 0.0000454. Okay, one more here. There's no zeros involved in this one, but there's a decimal here. This is just to emphasize the idea it's not going to the first non-zero number. It's going all the way to the ones position. So 1, 2, 3, 2.445 times 10 to the 3. So when we start talking more about significant digits, say we had 2 significant digits to round this here, it just means 2 digits in this case. I can't really round that to 24. It'd be a completely different number. but I can round this to 2.4 times 10 to the 3. So it's applicable for rounding. Okay. We're just going to do the opposite. Going to go to expanded notation here. So 5.33 times 10 to the 8. I'm going to write 5.33. And because this is a positive, it was a big number. So let's make it big again. 1, 2, 3, 4, 5, 6, 7, 8. Going to fill in all the zeros there. To get a sense for that number, that'd be 1,000, be a million. So 533 million. Pretty big number. And the next one here is 6.7. Because it's a negative, it's a small number, so we'll move it the other way. 1, 2, 3. There's the decimal. 0.0067. And then for the last one here, 8.91 times 10 to the 2. 8.91 times 10 to the 2, 1, 2. Just 891. So hopefully that's familiar. Probably the most that we're going to be using scientific notation is entering in your calculator. So I did put a couple tips here on how to use your calculator before you move on to the practice questions. A really big one that you should be using all the time is don't retype numbers in your calculator once you get an answer. Just press second minus and it gives you the previous answer. So for example, if I had 52.8 divided by 6.23 and I get a big long answer, I don't want to have to type that in again as 8.475 and spend all that time. So instead I just press second, the top blue button there, and then minus, and it presses answer. That's putting that same number back. You don't have to type it in. It keeps all those digits. So just hit enter, show that it is the same thing. And so I went second answer and I need to times that by 3. It's a lot easier than retyping. So hopefully you use that already, but if not, that will make things a lot easier. Second, if you made an error in your calculation, press second, enter, and you're going to get the same equation back. Meaning that if I wrote in brackets 85 minus 96 squared, and I got the answer, it was actually 85 minus 92 instead. Then I'm like, I don't want to have to retype that again. Let's just go real quick, second, enter, and it brings up the same equation, but I can go back now, change that to a 2, and get my spot. So that can be a faster way to use your calculator as well. The second last one here is for scientific notation, and it's using the E button, which represents times 10 to a multiple. And I gotta recommend you use this every time. You might already be doing all these things, but they are very useful for typing in lots of calculations. Let's go to the calculator. If I was gonna write 4 times 10 to the 3, I wouldn't want to do 4 multiplied by 10 to the exponent 3. I'd rather you not put it in like that because it handles it as 2 separate things, 4 and a 10 to the 3. So instead, just hit 4, second comma, that E means times 10 to the, and then you put 3. You don't need to put any exponents, no times 10, anything like that. And we can see it gives us that value. Makes it a lot easier for multiplying large numbers. So if I do 7.2 times 10 to the 14, okay, for example, multiplied by 5.6 times 10 to the 7, it handles it a lot better. It doesn't take the 14 and think that's what's getting multiplied by 5. The E keeps them grouped as values. Okay, if you want to throw brackets, sometimes I do just to be safe. It should give you the same answer, but for some reason, just to keep it clear in my head, sometimes I throw brackets. They're unnecessary, but it should still give us the same. Let's just double check. Yeah, it gives us the same thing. So really the E is keeping it already in brackets there. For visual, I like to put the brackets in so I can make sure I put each number right, but that's the point of the E. It keeps them separate and keeps your calculator doing it correctly. And the last little note here is to remember to use brackets around numerator and denominator. So if you had 5 plus 4 divided by 2 times 3, we have to remember that there are brackets on the top and bottom. 5 times 4 would be 9. 2 times 3 would be 6. I would get the answer 1.5. I know that's what I'm looking for. So going to the calculator, if I enter it just like that with brackets, 5 plus 4 divided by in brackets 2 times 3, I do get the 1.5 that I'm expecting. If you don't put the brackets around it, 5 plus 4 divided by 2 times 3, you can see it doesn't give us the right answer. So make sure we put those brackets in the top and bottom. And that's it. I know it was a little bit of a lengthy lesson, a little bit different getting it over a video, but I hope that worked okay for you. Give just these couple practice questions a try. We'll take these up once I come back. Hope you have a good rest of your day, and we will see you in the next lesson.